All right, we are getting ready for our last one of the year. So, this is about electrolysis and Faraday's law. So, you've probably heard me talking about electric potential and things and seen some of these, what do we call them, units and things. Here's what they all really mean. So, current is the number of electrons that flow through a system per second. These are called amps. AMP, capital A is the symbol for it. These are coulombs per second. A coulomb is the amount of charges, so amount of charge. That is a huge amount of electrons per second. So the idea is that the electrode surface area dictates the number of electrons that can flow. Larger batteries produce larger currents. Other electrochemistry terms. A volt. Volt is potential difference. This is the potential energy between them. 1 volt is equal to 1 joule per coulomb. So 1 joule of energy per coulomb of charge, which is that ridiculously large amount of electrons. This is the voltage needed to drive electrons through an external circuit. EMF you've seen before is electromagnetic force, electromotive force. Amount of force pushing the electrons through the wire. So we have the idea an amp is a coulomb per second, so many electrons per second. Volt is a joule per coulomb. Faraday is so many coulombs per 1 mole of electrons. So we can see there's a lot of variables in here that we can cancel out, convert, and change into different things. So an example that would come up in something like you're trying to electroplate or create from a solution into get an amount of mass, how many minutes does a 4 amp current need to be applied to a solution to make 15 grams of copper? Well, 15 grams of copper is what we're going to try and make. So we start with 15 grams, you got your molar mass. You have the idea that this is copper 2 plus, so for 1 mole of copper, you need 2 moles of electrons. 1 mole of electrons is equal to Faraday's coulombs. 4 coulombs per second, because that's the amps. And then 60 seconds for 1 minute. So it's going to take you, a little over 3 hours in order to get that. Now, just like all other calculations, lots of pieces, you can be solved many different ways. So recognition is the key. Practical ones are things like time, amounts of substance. Others could be determining proper current for that time. So like if I needed to do this amount of mass in this amount of time, what's the amps I'm going to need? Like that kind of stuff. You can go at many different ways. And then they could be like number of electrons and number of moles of electrons. Things that aren't very practical, but heck, they could be asked because you can figure it out. These are often for electrolytic processes. Remember, they're not spontaneous, have a negative cell potential, positive delta G. This is where we have something called electroplating and electrolysis. Electrolysis, using energy to break a compound apart. Most common one that you're going to come across is with water, making oxygen and hydrogen gas. Electrolytic cell, where you have an external source of energy. Separate elements from their compounds. Again, you have from the anode, water becoming oxygen with its hydrogen ions and electrons. Water breaking apart to produce hydrogen gas and hydroxide ions. Anode, oxidation, right? Because these have some where this is becoming oxidized. Loss of an electrons. And cathode is the reduction, gain of electrons. Okay. So the electrolysis of water, if we were to look at that, anode reaction, where we have it being oxidized, negative, where it's being reduced, negative. And again, your E should be negative, therefore not spontaneous. That's why you throw the electricity through there in order to have it work. The other place where this occurs is the electroplating of silver, where we're trying to get a metal onto there. So let's take a moment to look over this setup of this electrolytic cell. So in this case, you can see that we have both anode and cathode in the same substance. We really don't have much of a difference in concentration, maybe locally around each, but those will be mixed out throughout the concept here. But otherwise, this would have a zero source of voltage because it's the same substances in the same solution. But when we add a source of current through this, we have the cathode here, which is going to be a place where we're going to go from a positive charge to the metal. So therefore, that's going to be a reduction. And then we're going to have 0 to the metal to the positive charge would be oxidation. Again, anode is going to be oxidation. Cathode is going to be reduction. We need to have some, of course, requirements. Solution of the plating material, plating metal. So it needs to have silver ions and then some inert type of ion, something like a nitrate. Anode must be made of the plating metal. Cathode with the object to be plated. So the cathode doesn't need to be silver, something else, some other kind of metal. Generally, aluminum, steel, something that's not so special. And then it needs to have a source of current. Again, kind of a little fancier idea here. Object that's going to be plated. We can see the silver ions are going to become silver metal, and the silver metal is going to become silver ions. The workpiece is the cathode. Again, cations are reduced at the surface of the workpiece. The anode is made of the plate metal. Oxidizes replace the metal cations. Just a fancier picture. Flow of electrons. So again, battery is going to tell you if it's electroplating or an electrolytic cell. A voltmeter is going to tell you it's a galvanic cell. So the last bit, solving an electroplating problem. How many seconds would it take to plate out 5 grams of silver using a 20 amp current? So again, 5 grams, molar mass. This is a 1-to-1 ratio because we only have 1 electron. Faraday's constant. 20 coulombs per second. You need to understand that being amps. And it's going to take us, 220 seconds in order to get that because we're using a pretty strong current. All right. So that's the end of our year. It's been fun. You have... Take my hat off to you, and I hope you have a good rest of your year. Let me know what kind of questions you have. Take care. Bye-bye.